on here, chapter 8, I believe. So last time we talked about really kind of a couple of important conversions that we use in chemistry, one maybe more than the other. But that was the idea of moles. And remember that moles really represents in chemistry a certain quantity of a substance, kind of like what we talked about when you take something that's 12, and it can really be a dozen of anything: roses, donuts, flowers, whatever it may be. When we say a mole, it does also represent a sort of numerical value, and that numerical value is basically Avogadro's number. So 1 mole of anything equals 6.022 times 10 to the 23. And when we talk about the units associated with this, for the most part in chemistry, it is atoms and molecules that we use a lot. We can use any units, but really atoms and molecules do come up the most. It really is sort of our conversion factor to go between really those units. So if you have moles and you want either atoms or molecules, we use Avogadro's number basically to do that. And that's obviously what this number represents, Avogadro's number. And it is a constant value. It is a value that you sort of always have available to you. So you could always use it as a conversion factor, and really just writing it one of two ways: either a mole of something over 6.022 times 10 to the 23 atoms, or Avogadro's number there, 6.22 times 10 to the 23 atoms over a mole. Really important, again, to make sure that you do use your exponent button when you're using Avogadro's number. We also talked about the idea that sometimes people like to use Avogadro's number in every calculation, and a reminder that you should really only use Avogadro's number if it has something to do with atoms or molecules. Again, either they give you a number that's in atoms or molecules, or you're asked to sort of solve for something that's atoms and molecules. And also a reminder that when you do see MOL here, that does represent moles, not molecules. So again, a very common sort of mistake that sometimes people make. The other maybe more important, I guess, in a sense, sort of conversion factor that we use, that we talked about, is really molar mass. And the molar mass of a substance always has units of grams per mole, and it always has those 2 units. And as we talked about, the number that you get will always stay with the grams, and it's always 1 mole of something. And really, we can get that number from the same place from the periodic table where we get atomic mass. And numerically speaking, the atomic mass in AMU per atom, which is essentially what you could grab those numbers off the periodic table as, is the same as the molar mass in grams per mole. So they're basically the same number that you could get from the periodic table. Thank you. So we could do anybody up there, like if we looked at nitrogen there, 1401, we could pull that off as our molar mass. And once again, what that would mean is that there are basically 1401 grams per mole, and nitrogen would be the molar mass. And just like anything else, we could use it in dimensional analysis approach and do it as a conversion factor. We could say 14.01 grams per mole of nitrogen, or a mole of nitrogen is 14.01 grams. So molar mass is really one we use a lot to really do, obviously, these conversions here, going from grams to moles and back, sort of moles to grams. A lot of chemistry calculations, the first step that you do is basically grams to moles, is sort of the very first step that you oftentimes will do. We also could do it for some type of compound as well. You could just add up the parts. You know, if you had something like this, you would go to the periodic table, find carbon, you would find hydrogen. And again, here we would just add up the parts. So there's 2 carbons, each at 1201. And we have 2 hydrogens, each at 1.008 grams per mole from the periodic table. Gives us about 2604 grams per mole would be the molar mass of C2H2. So, if it is some type of compound, you basically just do it. The other important thing with molar mass, as we'd also talked about, is it is always per mole. And what that means is you should always, if you are going to calculate the molar mass of something, simply just take the formula by itself. So just the individual formula by itself, one of them, go to the periodic table and add up all the parts basically to get the molar mass. Any question on any of the stuff we talked about last time here? All right. So why don't we pick up with this example here? We're looking for how many moles of ethanol are there in 23.2 grams, and also how many molecules. So basically two answers here, starting with the same grams. Give you some numbers that will be helpful. Carbon 12.01 on the periodic table. Hydrogen 1.008. And oxygen is 16. All right, take a minute here, see what you calculate, see how we're doing. So in the first one, we're starting with grams and we are going to moles. So we are basically going from grams to moles. Remember that conversion is really our molar mass from the periodic table, right? That is basically where we get that from. For the second one, we're then going to go really from moles. We can pick up to molecules. Then we're going to kind of go into molecules. So remember that the moles to molecules conversion is really Avogadro's number. So that's sort of our pathway to sort of get us to the answer. That means starting with the first one, we do need the molar mass. And again, we would go to the periodic table and we're just going to add up all the parts. So there are 2 carbons, each at 12.01. We have 6 hydrogens, each at 1.008. And we got an oxygen at 16. So again, just basically adding up our parts, that's our carbons, that's our hydrogen mass, and that is our oxygen mass, basically. And if we add up all that together there, we end up with a number probably that has numbers with it. 4607 looks like. And that would mean that there are 4607 grams per every mole. And again, we're going to use that as a conversion factor. We're going to start with the 23.2 grams of our ethanol here. We're going to do a little dimensional analysis and opposite of units. So grams are up on top, means that grams need to go on the bottom here to cancel. We are basically dividing by the molar mass here. And when we do that, the grams obviously here will cancel. Taking 23.2 divided by 4607, going to get us a 0.504 moles here of C2H6O, since we are looking obviously for an answer. Any questions on that calculation there? At this point, we could actually just continue on, since we're starting with obviously the same number of grams, which would give us the same moles, to go into molecules. So here we would use Avogadro's number, where 1 mole of our C2H6O would equal 6.022 times 10 to the 23. And these would be molecules in this case. That's going to be our conversion factor to continue on. So I'm going to pick up here with the rounded number here, since we did get an answer, 0.504 moles of C2H6O. Once again, a little dimensional analysis approach, our moles are up on top, which means the moles need to go opposite to cancel. So they're going to go on the bottom. And our Avogadro's number in this case will go up on top, which will give us molecules. The moles will cancel, and if we multiply it by Avogadro's number, making sure we use again our exponent button, looks like 3.03 times 10 to the 23rd molecules here of C2H6NO. Any questions on any of those steps there? Clearly, if we were just going straight from grams to molecules, we could just bunch the calculation together and continue on. Just for calculation purposes, even though I did round the first answer, I kept the whole number on my calculator and continued on for the second part of the question. And again, as we talked about, if you do get a number and then continue on, You don't want to really round too much, but in this case, we did have to give the answer, so we had to do a little bit of rounding. Any questions on that there? All right, let's try one more here, maybe. What is the mass? In case we're actually starting with molecules, and we eventually want to get over to grams. Really, the one that ties both of those together is moles. So our pathway, once again, is molecules to moles using Avogadro's number. We'll do that. And again, moles back to grams using the molar mass from the periodic table. So we can start with the first part first here, which is 1 molecule of C8H10N4O2. Could it be any longer? All right. So here we want to use Avogadro's number, which again is our mole is equal to 6.022 times 10 to the 23 molecules. Here we want to get rid of molecules. So in this case, we're going to put Avogadro's number on the bottom, which is opposite. And up on top would go 1 mole of our C8H10N4O2. I ran out of parentheses there. At this point, if we stop the calculation, the molecules here will cancel and we'll be left with moles at this point, which basically gets us to here. So once again, to go from moles to grams to finish the calculations, that is the periodic table and the molar mass to do so. So once again, here, we're just going to add up all the parts. There are 8 carbons, each at 12.01. And there are 4 nitrogens, each at 14.01 from the periodic table. And lastly, here, there are 2 oxygens, each at 16 from the periodic table. Doing all that together, 194. Any questions on where I got the numbers from? We kind of have a converter. So following our dimensional analysis approach here, we have moles that are up on top. That means moles need to go in the opposite location on the bottom so that they cancel. And the grams here will actually go up on top. The moles will cancel, leaving us with grams. We're basically multiplying across the top there, which is really just 194.2. We're coming back and dividing by what's on the bottom using our exponent button, 6.022 exponent button, and 23. And that gets us something like 3.225 times 10 to the minus 22 grams of our guy here. Any questions on that calculation? Yeah.
Starting off with that, would that not be right? Like using 194.22 molecules and doing 1 gram.
You probably want to start with the 1 molecule as what was given to you, and because you want to end with grams. So you would want to save that for the end part of the calculation in this case. So you would definitely probably want to start with the molecules. Yeah. Other questions? No. Sig fig wise, there's really not much sig figs going on there. There's 1 molecule, which is technically like an exact number. If you had 1 of something, you would just count it. Like if you had 1 bottle, you just count, you have 1 bottle. So you technically is an exact number, which means you can do as many sig figs as you want. I just did 4 molar mass here in terms of 4. Any questions on any of that there? All right. One last thing here I want to talk about in terms of this is, let's say we had something like we wanted to know how many carbon atoms there are in 46.5 grams of C4H10. So in this particular case, there's a couple of things that's happening here. First off, we're actually interested in just carbon, right? Just C. We're not really interested in the whole entire thing, which is C4 H10. So we do need a way to kind of go from like the whole thing to just the carbon part. And sometimes you are asked about kind of individual elements within a formula. So we actually could use the formula itself as a conversion factor. So you could use the formula as like a conversion factor to help you do that. When we look at these numbers on the bottom, they can represent the moles of each of those guys, as we'll talk about a little bit later on here when we talk about empirical formulas and all that good stuff. And we can actually come up with a couple of relationships from the actual formula itself. We could say in 1 mole of the entire thing here, there is 4 moles of carbon. And that simply is just a little subscript that's next to carbon. And we could also say in 1 mole of the entire thing here, there would be 10 moles of hydrogen. So this is a way that we could actually use the formula itself to just focus in on one particular element that may be there. These are obviously like a mole to mole relationship, which means in terms of units, the first thing we would have to do is actually convert these grams into moles so everything cancels. So we want to convert the grams of the whole thing into moles. We would need the molar mass of C4H10, and that would be 4 times 12.01 grams for the carbon and 10 times 1.008 grams per mole for the hydrogen. And that's going to give us a molar mass for this thing of about 5812 there, I think. So the first thing that we'd want to do in this calculation is really just kind of get it into the right units. So we would start with the 46.5 grams of C4H10 that was given to us. Using the molar mass here, we're going to divide by the grams. So 58.12 grams per mole of the entire thing. At this point, the grams of the entire thing cancels. And if I stop right here, I'm in moles of the entire thing. Because now I can use my relationship here that I got from the actual formula and go from moles of the entire thing to moles of just carbon in this case. And that's what I would do next. I would take the moles of the entire thing, which is from the equation, our formula, 1 mole of the entire thing is equal to 4 moles of just carbon. At this point, if I cancel out the moles of the entire thing, I am in moles of just carbon. I'm almost to where I need, right? But I do want atoms of carbon, which means what should I use to get me there? Yeah, so here we would go from moles to atoms using Avogadro's number. So that would be the last step that we would need to do in this case. Again, we would want the moles to cancel. So the moles would go on the bottom. And Avogadro's number there would go up on top. The moles of carbon would cancel. This case, we're going to multiply everybody up on top, right? And come back and divide by everybody that's basically on the bottom, which is really just the first guy. So if we do that, that's 46.5 times 4 times 6.022 to the 23 divided by 5812, going to get us something in the ballpark of 1.93 times 10 to the 24 atoms of carbon are in this guy. Any questions on that calculation? We obviously could do a similar calculation relating hydrogen in this case. It would just be a 1 to 10 relationship in terms of the mole relationship. We also could have, if we wanted to, not figure out atoms, but we could have figured out how many grams of carbon would be there, right? And if we wanted to do something like how many grams, we would substitute the molar mass of carbon into that spot, and that would give us, right, how many grams of carbon that would represent. So, you know, there's a few different ways you can do it. So sometimes in these type of problems, you may be asked for just a particular element by itself, not the whole thing, but you can potentially use the formula as a conversion factor to allow you to go really from the whole thing to each individual element. Any questions on that aspect of it? Any questions on grams, moles, Avogadro's number, any of those things? Okay, then let us continue on then. So we're going to talk a little bit about different types of formulas here. Molecular formula. The molecular formula obviously is the representation of a molecule. It is, as we will talk about here, basically tells you exactly how many of each element are present. So when we see the molecular formula, it pretty much exactly tells you what's there. A chemical formula expresses the composition of a compound. We use obviously the symbols. We use our subscripts. So a reminder, right? When we see a formula like this, the subscripts go to the guy to the left. And a reminder that if we do not see a number, it represents one, right? So if you don't see a number written there, it does represent one of those. And as we just saw, one way you can use those numbers is as the moles of each of those elements that are present in a compound. Now, the molecular formula, like I said, does give you basically exactly what's there. And the simplest molecular formulas that we have are really for our diatomic molecules like H2, N2, O2. Now, molecular formulas can be just basic of this is what's there. But it also could give you some information about how things are connected. And sometimes people see different molecular formulas for the same thing and think that they are sort of different compounds, but they are the same. So for example, if we look at ethanol here, for example, that is C2H6O. That is one way that you could represent it. It tells us that there are 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom present. This formula here, where we have CH3, CH2, and OH, is also ethanol. It has 2 carbons, it's got 6 hydrogens, and it has 1 oxygen. The difference is that one gives us a little bit more information about how everybody's sort of connected to each other. If we were to draw ethanol, it would look something like this. And as you can see, you can pretty much, that is CH3, that is CH3. This is CH2, that is CH2, that is OH, that is OH. So again, the one on the right there gives us a little bit more information about structurally how it's put together. That's also why it's sometimes called a structural molecular formula, because it does give you that structure sort of information that you maybe not get from just the first. So be aware that as you on bottles and stuff like that, that sometimes happens. People go, it's like different formulas, these different things, and sometimes they are the same thing. An empirical formula is an important formula. An empirical formula is the simplest whole number ratio of what's present. So it is, as it says there, the simplest whole number ratio of what elements are basically present. So, for example, if we look at something like hydrogen peroxide, which is what we see there, H2O2, that is basically 2 hydrogens for every 2 oxygens. That is the same as a 1-to-1 relationship. You divide everybody by 2. That means that the empirical formula here for something like hydrogen peroxide would be HO. If we did our C4H10, if this was our molecular formula, that is basically 4 carbons for every 10 hydrogens. You could actually reduce everybody down by 2 here. That's the same as 2 carbons for every 5 hydrogens. And that means that we end up with a C2H5 as its empirical formula. So it does have to be whole numbers, the subscripts. You can reduce down it by dividing by a common number, but when you divide, you got to still hit whole numbers for everybody on the bottom. So if you can't do that, In certain cases, the empirical formula and the molecular formula are the same. So if you have something like water, water is 2 hydrogens for every 1 oxygen. There's no way to reduce that down and still get another whole number. So H2O is both the molecular formula and also the empirical formula as well. All ionic compounds are always empirical formulas. So when you have an ionic compound, they are always empirical. So for example, when we take something like a sodium ion and a chloride ion, when we put it together, the simplest way to get to 0 is 1 of each. That is why when we write the formula for sodium chloride, it is NaCl. You could obviously get to 0 many different ways, like taking 2 of each of these, and that would equal 0. But that is not the simplest whole number, because you could then reduce each of these down by 2 and gives you the proper empirical formula, or formula there for sodium chloride. So all ionic compounds, when you put them together, the positive and negative guy together in the simplest way to get to 0, will always equal 0, and it will always be really the empirical formula that occurs. So here's another example, N2H4. Again, there's 2 nitrogens for every 4 hydrogens. We could reduce that down by 2, gives us NH2 there for our empirical formula. Remember, it is only the molecular formula that really does tell you exactly what's present. The empirical formula may be able to do that if it's one of these guys, for example. In each of these cases, these guys are pretty much reduced down as far as they could go. Could not reduce them down any further. So they are both the molecular formula in each of those cases and also the empirical formula that is there. Any questions on that there? So take a second here and figure out the. Okay, let's take a look here. So obviously here in the first case, we got 2 carbons for every 2 hydrogens. That basically is the same thing as a 1-to-1 relationship. You could obviously divide it out by 2. That gives us a CH as our empirical formula. For the second one there, that is 2 iodines for every 5 oxygens, and that is pretty much as low as you could go. No way to get a whole number by dividing out anything. So that means this would also be the empirical formula as well. And lastly here, glucose, that is 6 carbons to 12 hydrogens to 6 oxygens. We really could reduce everybody here down by 6, right, to get whole numbers, and that would get us CH2O as our empirical formula. Any questions on any of those there? Okay, so let's talk a little bit about percent composition by mass. So the percent composition by mass of a compound basically allows you to calculate the percentage of each element that's present in a particular compound. We basically calculate it by taking the percent composition would equal the mass of the element that's in the compound divided by the molar mass of the compound, and then times it by 100%. So very similar to what you did the other day when you calculated the percentage of water that was in your formula. You got the molar mass of just the water, you divided by the molar mass of the entire compound, and you times it by 100. So very simple here. That's basically what you do. Take the mass of each individual element divided by the mass of the whole thing, times it by 100. So let's take a look at one here together, H2O2. So to do this, we first obviously would want to get the molar mass here of hydrogen peroxide. So that is 2 times 1.008 for our hydrogen, plus 2 times 16 for our oxygen. That is going to get us a molar mass for hydrogen peroxide here of 3402. So to find the percentage of hydrogen here, we would take the mass of hydrogen in the formula, which they would be 2 times 1.008 divided by the molar mass of the compound here, 3402 grams per mole times 100%. And if we do that, we end up with 5.926% hydrogen. This guy is about 5.926% hydrogen. We could do the same thing for our oxygen here. Our percentage of oxygen would be, we also have 2 oxygens here, which would be 2 times 16. Again, from the periodic tables where we get that number, divided by 3402 times 100%. And in this case here, we would get 32 divided by 3402 times 100%. Gets us 94.06% oxygen. Yeah. Any questions on that one there? By the way, when I add up this percentage, it should add up to 100%, right? If that's all the elements that are present. That also meant that, technically speaking, after I got this percentage, since there was only one other element, I could have took 100 minus that, right? And got the second percentage. That would work a lot easier too. So sometimes that's quicker. But you could do it obviously the other way as well. Any questions on that there? So this is H2O2, which is the molecular formula for hydrogen peroxide. Let's take a look at what would happen if we did the same percentages there for our empirical formula. Would they be the same or would they be different? So let's take a look and see. So if we were going to calculate for the empirical formula for the same guy, basically, we would get the molar mass, which in this case would be 1.008 grams per mole plus 16 grams per mole. That gives us a molar mass for our empirical formula here of 1701. So if we were to calculate the percentage of hydrogen here, we would take just the one hydrogen in this formula. We would divide it by 17.01 grams per mole times 100%. And we end up with 5.926% hydrogen. We'll do it the long way here for oxygen. Same thing, 16 grams per mole divided by 17.01 grams per mole times 100%. Gives us 94.062. Oxygen. Are the percent composition by mass the same or different? They are the same. So they're the exact same as what we calculated from the molecular formula as to what we have in the empirical formula. And again, that's because they are related to each other. The empirical formula, again, is the simplest ratio of what's present. So it's the same ratio, basically, which means they have the same percentage of mass of each of those elements. Any questions on that there? All right, so let's try one here for yourself here, perhaps. What is the percent composition of each of the elements here in phosphoric acid? So hydrogen 1.008, oxygen 16, and phosphorus 3097. Compound here, so that is 3 times 1.008 for our hydrogens. We're going to add that to 3097 for our phosphorus, and 4 times 16 there for our oxygens, giving us a molar mass of, I think, 97.99 grams per mole, I hope. Any questions on that there? So we'll start with our first one there. We'll do our percentage of hydrogen in this case. And that would be 3 times 1.008 which is the mass of the hydrogens that's there, divided by 9799, which is the overall molar mass, times about 100%. That will get us 3 times 1.008 divided by 9799, negative, times 100. Looks like 3.086% hydrogen. We do the same thing here for our phosphorus. So there's just one phosphorus, so that would be 3097 up on top, divided by our 9799 times 100%. And at this point here, we would take 3097 divided by 97.99 times 100, going to give us about 31.61%. We'll call it 31.61% phosphorus. Lastly, here we could also do the oxygen the same way, 4 times 16 grams per mole divided by 97.99 grams per mole times 100%. And in this case here, about 65.31% oxygen in this case. Any questions on any of those calculations there? Again, if we add all those percentages together, they approximately should equal 100%. Might be a little less, might be a little bit more, but with rounding, it should be in the ballpark of 100%, which they did. Also, like we talked about before, you could have done the first two, added them together, and then also subtracted from 100 to get the last one. Again, that's another way you could have done it. Any questions on percent composition by mass? All right, the next thing we're going to talk about then is actually how to calculate an empirical formula. So let's say you're not given the molecular formula, but you're given some information about the compound. And a lot of times the information that you're given about the compound is actually this information right here, which is the percent composition by mass of each of the elements. By the way, in this case, this is mainly made up of oxygen, right? Followed by phosphorus and a little bit by mass of hydrogen that's present. So there are several steps that you follow to calculate an empirical formula. So to calculate an empirical formula, you basically convert percentages, if you're given it, to mole onto grams. And when you have a percentage that you want to kind of convert into a number, it's usually good to assume that you have 100 of it, right? So a lot of times we'll assume that we have 100 grams. What that essentially does is keep the percentages the same numbers, just turns them into grams. You just change the unit. Once you have everybody in grams, you then want to convert to moles. And that, once again, is our molar mass from the periodic table to do that, like we've been doing. Once you have everybody in moles, you divide by the smallest number of moles. So let's just say, for example, you did step number 2 and you yielded 2 moles of A and you yielded 4 moles of B after you did step number 2. What you would do here in step number 3 is simply divide everybody by the smallest number of moles, which is 2 in this case. So you would divide everybody by 2. This would give 1 for A. This would give 2 for B. And if you do the actual whole number on both of them, that's your empirical formula. So our empirical formula here would be AB2 in this example. By hitting a whole number means you actually hit a whole number or you're super close to a whole number. So in a textbook problem, you basically need to be really, really close to a whole number in order to round. There's not a lot of rounding that happens usually in textbook problems and stuff like that. Like if you're like 1.99, 1.98, you're like 1.97, you're kind of really close to 2. That's pretty close. Or if you're like just over the number, like 2.01, 2.03, you know, something like that, that is really close enough to round. But if you find yourself with like a decimal that's really not close to the number, like a 0.25, 0.5, 0.33, something like that, that is too far to round. So in situations like that, we do not round. We have to sort of figure out a number to multiply everybody by to get to a whole number. So for example, if we got to step 2 and we did step 2, and in that case, we had 2 moles of A, but 5 moles of B. when we would go to divide by 2 in this case, what we would end up with is 1 for A and 2.5, I hope on my math there is right, for B. And that would give us an empirical formula of A, B 2.5. These numbers, which are on the bottom, which are the moles and the subscript, they got to be whole numbers. You can't have like a half a B, right, hanging out there or anything like that. So they do have to be a whole number. Something like 0.5 there is too far to round one way or the other. So what we have to do is go, all right, well, 2.5 times 1 is like 2.5. If I take 2.5 times 2, that is 5. So 2 would be the factor by which I would want to multiply this empirical formula by to get a whole number. The key here is you're multiplying everybody here, both guys in this case, by the 2. So you would multiply 2 times this, and that would give you A2, B5 as my proper empirical formula. So sometimes you really don't hit a whole number when you divide, and you got to find a multiple to multiply everybody by that will turn them into a whole number. Common endings where you should not round, you know, like 0.25, 0.5, 0.33, so forth. Those are common endings where you should find some type of factor to get to a whole number. Any questions on that there? So let's run through one here together to show you how to calculate an empirical formula. So let's take this one right here. We want to calculate the empirical formula of vitamin C. It's basically made up of 40.92% carbon. It's made up of 4.58% hydrogen, and it's made up of 54.50% oxygen. So these are the percent composition by mass like we were just talking about. The first thing you should really always do is just take a quick look at the percentages and make sure it adds up to 100 or pretty close to 100, which it does in this case. If it did not add up to 100, you're definitely missing an element somewhere. Yeah. So because it all should add up to 100. So you would obviously have some way to figure it out what's missing, but you know, something would be missing in that case. In this case, since it all does add up to 100, the first thing we want to do is convert these guys into grams. So basically what we want to do is assume that we have 100 grams. And all that's going to essentially do is just keep the numbers the same. So that's going to mean that we would have 40.92 grams of carbon. That means we would have 4.58 grams of hydrogen, and we would have 54.50 grams of oxygen. So really all we did there is just kind of convert our percentages into grams by assuming 100 grams. The next thing we want to do is take our grams and convert them into moles. So we're going to divide by the molar mass of carbon, which is 12.01 grams per mole. We're going to divide by the molar mass from the periodic table of hydrogen, 1.008 grams per mole. And we're going to divide by the molar mass of oxygen from the periodic table, which is 16 grams per mole. So that's going to give us basically the moles of each element that are present. So if we do 40.92 divided by 12.01, we end up with 3.4072 moles of carbon. We take 4.58 and divide it by 1.008. We end up with 4.544 moles of hydrogen. And lastly here, 54.5 divided by 16 gives us 3.406 moles of oxygen. At this point, once we have everybody converted into moles, we're going to divide by the smallest number of moles in this case. And in this case, it is just the smallest number. So they're pretty close, this one and this one, but it looks like the oxygen just beats it out. So we're going to divide everybody here by 3.406 moles. And divide this guy by 3.406. And we're going to divide this guy by 3.406 moles. That gives us about 1 there. That definitely gives us 1 there. And when we take 4.544 and divide it by 3.406, we end up with 1.33 in this case. Any questions on that so far? Now, at this point, our empirical formula would be CH 1.33 and O. Is that an okay empirical formula? It is not, because they're not all whole numbers. So this number here, which is 0.33, is too far away to round. So we need to figure out a number to get us to a whole number. So you could just do trial by error. 1.33 times 1 is obviously 1.33. 1.33 times 2 is 2.66. 1.33 times 3 is 3.99, and that's pretty close to 4. So here, what we would want to do actually is use the factor of 3 and multiply all those numbers by 3. And if we do that, take 3 and times everybody there, gives us C3H4O3. And that would be our proper empirical formula. Any questions on those steps? So once again, convert to grams, grams to moles, divide by the smallest. And then if you hit whole numbers, you're done. If you don't hit whole numbers, then you got to find a factor to fix it with. Any questions on that there? Okay. So I think I'm going to stop there actually right now.